Log on, tune in, find out. Another good idea from Cambridge.
Our speaker this morning is Ivan Losev, speaking on irreducible finite dimensional representations of W-algebras.
Thank you. First of all, let me thank organizers for inviting me to this conference. And also let me give you some plan. So first of all, I want to state results. Then I will briefly recall definition of W-algebras. Describe whatever this means, maps between sets of ideals. And time permitting, I will make some remarks. Okay. So the setting is as follows. I have some algebraically closed field of characteristic 0. This is my base field. Then I have a semi-simple Lie algebra. Well, say E8. I fix some nilpotent element, non-zero. Don't pay attention to this. And to this data, I can assign a certain associative algebra, which is called finite W-algebra. And this can be defined, as John Brandon explained to us, like UGE is UG modulo UG M tilde invariance. Well, actually, this is one of possible definition, and this is not a definition I will use. Just, to give some definition from the beginning. Okay. Now, the question I want to consider is the relation between two sets of ideals. So goal, construct maps between well, I have some finite codimensional ideals in UGE. This is ideals, two-sided ideals of finite codimension. And on the other hand, I have ideals in the universal enveloping algebra. Such that their associated variety, well, let me recall that associated variety is just set of zeros of the associated graded ideal equals the closure of the orbit of E. So I want two maps between these two sets of ideals. And from properties of this map, of these two maps, I will extract a relation between primitive ideals here and primitive ideals here. So let me recall that ideal J is primitive if it is annihilator of some simple module. So let me state the result. Let PR fin of UGE and PR E U of G be sets of primitive ideals. In the corresponding sets. Then the main result, which was conjectured by Sasha Primet, and proved by myself last year, is the following. So we have the component group of our element, and this group acts on the set of primitive ideals in the W-algebra. And it turns out that the quotient for the section is nothing else but the set of primitive ideals for U of G. I always stick to primitive ideals whose associated variety is this. So that's the main result. Yes, thank you. Okay. So let me explain how these two maps look like when we use definition above. So remark. So if we have some ideal G, some ideal J in U of G, well, we can take Hamiltonian reduction like this. So we assign to it ideal J modulo J M tilde. That's an ideal in the W-algebra. And the way we go back is the following. We are given some ideal I in UGE. So from this, we produce some module, UGE module V such that annihilator of V is I. I take any module. Then I actually have what is called Whittaker equivalence. So I take the module U of G modulo UG M tilde tensor over UGE V. So let this be, I don't know, V tilde. This is a module over universal enveloping algebra, and I take its annihilator. It turns out that this is well defined. So these are two my maps. And one thing which is possible to see from this definition is that when we have started with primitive ideal here, we can take irreducible module here, and then, well, the corresponding tensor product functor is equivalence of categories. So we have irreducible module here. So perhaps. So indeed, this mapping maps primitive ideals to primitive. And it turns out that this map induces isomorphism above. Okay. Now, the problem with this definition is that I don't know how to prove the theorem using it. I will need alternative definition of this map. And first of all, I will need alternative definition of W-algebra. Well, first of all, let me recall you what Losev Lie is. Alexey Sevastyanov defined it yesterday. So we can take SL2 triple. And this SL2 triple allows us to define the Losev Lies like this. And actually, important thing about the Losev Lies is that it is equipped with two group actions. Well, first of all, there is an obvious group action. Let me denote by Q the centralizer of E, H, and F. This group obviously acts on S. This is some reductive group. And then I need an action of one-dimensional torus. So I have one-dimensional torus. And, well, in order to define the action, I need to define certain one-parameter subgroup. Well, I can embed k times to SL2. And I can map SL2 to our group G, corresponding to our Lie algebra. Well, the first map is just T goes to the diagonal matrix, like this. And then we have homomorphism induced by SL2 triple. In this way, we define some one-parameter subgroup gamma of our group G. Well, now by definition, Kazhdan action of k times on S is given by the following formula. So t applied to S small is t2 minus 2 gamma of ts. And one can easily show that this action indeed stabilizes this Losev slice. And the most important property of the action is that it contracts S to a point. So limit when t goes to infinity, t applied to S is just our origin point E. And this contraction property can be stated in an alternative way, namely the gradient on the algebra of regular functions is positive. Now, actually, I will need two more varieties. I will need variety G, the Lie algebra itself, and I will need a vector space which is image of ADF. Well, let me know that this vector space carries a natural symplectic form, constant Kirillov form. Now, these two varieties have similar group actions. So Q acts on G and V in a natural way. But also K times acts on G, well, the same formula, like here. And it acts on V. So to apply T to V is the same as apply gamma T. Okay, so what I have now, I have three varieties, each equipped with two group actions. And my goal is to produce quantizations of these varieties. Somehow, during the previous workshop, I spent one lecture producing quantizations. So let me recall very briefly what we have. Well, we have the following k h-bar modules, where h-bar, as usual, is a formal variable. We have module, which I will denote by W h-bar, which is polynomials in h-bar with coefficients in Ks in the algebra of regular functions on S. Then I have U sub h-bar, which is the similar gadget for G instead of S. And finally, I have A sub h-bar, which is the similar stuff with V. So these are k h-bar modules. And one can make them into algebras, into non-commutative algebras. So there are new structures of k-h-bar algebras. With respect to the product which is denoted by star. So, for example, star is like this. So there are some nice star products which are constructed in some way. I will not recall construction here. I will just recall two properties. Such that, well, first of all three stars are Q and K times equivariant. Sorry. Well, groups act as follows. So Q and K times act on Ks and the other two algebras as before. The actions are induced by these two actions. And, well, I want algebra homomorphisms, so I need to specify how these two groups act on H bar. So H bar is Q invariant, but the torus multiplies H bar by a character. So T applied to H bar is T squared H bar, where T is in K times. This defines two actions by automorphisms. And similarly for other two algebras. That's the first property. And the second property I will need is a property of being quantization, actually. And this property is just that, so if I write f star g, if I expand it in powers of H bar, where f and g in Ks, then d0 is just commutative multiplication. And an arbitrary di is bidifferential operator. Okay, these are two properties. There are some others, of course, but I will need these two. Okay, so far we have got three algebras like this. These algebras include parameter H bar. These are Jenin associative algebras. Well, but actually algebras I want to deal with from the beginning are not of this form. They are not algebras over K H bar. And so I will introduce three new algebras, which will be quotient. Questions? Which will be quotients by H bar minus 1. So I will have algebra W, which are W H bar over H bar minus 1, U H bar, U similarly, and A like this. Well, actually, this is a Weil algebra. So I don't have arbitrary star products. I have some nice star products. And with respect to this star product, this will become Weil algebra. Then U is U of G, universal enveloping algebra of G. And finally, this W is my W algebra. So this is not a definition of W algebra. This is just some reminder how this definition looks like. And finally, I will need 3 more algebras, which are completed versions of my algebras from here. I will need algebra of formal power series, which I denote by W-algebras. And this will be algebra of formal power series centered at E. So this is a formal power series. And then I take formal power series with respect to h bar. So this is algebra consisting of formal power series with respect to all variables. And now it carries non-commutative product induced from star. Which definition? Well, as vector space, it is like this. Image of ADF. Yes, that's just a vector space.
It's a tangent space to the
No, I'm
orbit
just
of F.
asking
at
what
F,
V
yes?
is supposed to be. The different lines.
Tangent space to the orbit.
Okay, so I have this algebra of formal power series with non-commutative product, and I have 2 similar algebras, which are UH wedge and AH wedge. Well, these are completions, yes. I need these 3 algebras, and the reason I actually need these algebras is that there is nice isomorphism between them. May I be of help?
At E, don't you?
Well, in V there is point 0, there is no point E.
You complete at E. At E.
Yes, here at E, and here, well, in 0. Okay, and the theorem.
Maybe just explain what completion is.
Well, you have some vector space, you have some point. Then you consider this point as origin. You consider this point as the origin and take all formal power series. You take some coordinates.
Or you can take the maximal ideal.
You can take maximal ideal and
complete with respect to power.
But these are all commutative algebras.
this is commutative. But then I deform product Well, actually, my DIs are,
IFS is supposed to be commutative.
yes, it's commutative algebra, and then I define product by this formula,
Yeah.
well, DI are by differential operators, so I can extend them to power series.
Yeah, or you can take a maximal ideal in those algebras and complete with respect to its powers. You will get the same.
Yes. So theorem is that there is Q times K times equivalent isomorphism. Let me denote it by phi sub h bar from UH wedge to the completed tensor product of the other two algebras. And this is the isomorphism of topological algebras over formal power series. So this means that up to appropriate completion, your universal enveloping algebra decomposes into the product of Weil algebra and W algebra. So, and somehow this finishes part 2, which was definition. And now let me describe maps between sets of ideals.
Last question. In this product, the tensor components commute, right?
Yes. So maps between sets of ideals.
So maybe this is a consequence of the fact that you have a vector space decomposing into subspaces and folds, right?
You need something that, you know, your non-commutative product also decomposes, which is quite natural because you can also, you know, this in a sense trivial, so symplectic, and you can always mod it out, but okay, so I'm interested in constructing two maps. I have two sets. I have a set of two-sided ideals in my algebra U, in my universal enveloping algebra, and in my algebra W. So these are sets of two-sided ideals. I want to construct maps between them. So I want to map in this direction and also in the other direction. And to this, I need to relate these two sets with certain sets of ideals in my homogeneous algebras, and then in my completed algebras. So let me do it. So I want four more sets. I want sets ID W sub h, ID U sub h, and corresponding sets for completed algebras. So these are sets of two-sided ideals. Say I sub h such that, first of all, so for my original algebras, I consider at the moment all ideals. Here I need two properties. Yes?
Sorry to understand this result. Your algebra, this Y algebra, it depends on the choice of this module V, yeah? Is it kind of particular choice of module or
V
is
is
it fixed?
completely
V is
fixed.
V, it's fixed, right?
V is fixed.
It's defined by F.
Okay.
Well, I need condition of being k times stable. And I need saturation condition. So IH bar is H bar saturated, which means that if H bar A belongs to I sub H, then A also belongs to I sub H. Okay. So I have 6 different sets of ideals, and now I need to relate them. Well, first of all, I claim that ID of WH is canonically isomorphic to ID W, as well as ID U sub H is canonically isomorphic to ID U. And if you want to map from here to here, well, you take I sub H bar and map it to the quotient of I sub H by H bar minus 1. And the other way, you have risk construction. I don't want to explain what it is. So these sets are the same. Now, secondly, ID WH wedge is the same as ID WA sub H. So the maps are, well, this direction. If you have I sub H here, you just take intersection with finite part. And the other way, it's completion. So you just take ideal and take its closure. And the reason why these maps are inverse, because gradient on Ks is positive. Now you can do exactly the same maps for ideals in algebras related to U. So you have maps from ID U sub H to ID U sub H wedge, and you have a map back. And now these maps are not inverse. So they are a priori not inverse, but actually they are indeed not inverse. Okay. And finally, ID WH wedge is the same as ID UH wedge.
And these maps are inverse in one direction, right?
Perhaps. No. They are not inverse in both directions, but in one direction for very stupid reason,
Yeah.
and in one direction for subtle reason. Let us discuss this later. Why is this? Well, because of the theorem. So theorem says that UH wedge differs from WH edge by multiplying by Weil algebra. And multiplication by Weil algebra doesn't change sets of ideals like this. So the map from here to here will be I sub H goes to the tensor product with the Weil algebra. Okay, now I'm left just with two sets of ideals. One set of ideal is IDU, and another set of ideals is IDW. And I have maps. Well, I have maps from IDW. Well, first I go to IDW sub H, then to here, so all three maps are bijections. Now I have the only non-bijective map. And finally, identification with IDU. And similarly, I have a map in the other direction. So this map I will denote by, so this is I goes to I with upper index dagger, and the other map J goes to J lower index dagger. This is from IDU to IDW. And let me recall that this map is essentially completion. So the only non-trivial map I have is completion here. And no, this map is completion, this one. And this map is intersection with finite part, intersection with polynomials. So you can think about it as follows. You have an ideal in a polynomial ring, you complete it, and you get an ideal in formal power series ring. Vice versa, you have an ideal in formal power series, you intersect it with polynomials, and get an ideal in polynomials. That's all what happens, basically. Okay. So I have two maps, but as you maybe remember, I wanted maps between different sets of ideals. I wanted a set of ideals of finite codimension in W-algebra, and ideals with support condition in universal enveloping algebra. But actually, so actually maps I constructed restrict to these two sets. So restrict to maps from ID fin W to ID sub E U. And as maps between these two sets, they have some very nice properties. So let me state the main theorem. So first thing I can do, I can take an ideal from here, go here, and return. And let's see what I get. So I take J in ID EU, and then what I claim is that J, well, lower dagger, upper dagger, well, this always contains J. This is pretty obvious. You complete it and then intersect it back. You of course have what you had before. Well, and maybe something else. And then, so they almost coincide. So the quotient is supported on the boundary of the orbit. So they may be not equal, but they are equal modular some small parts.
This is assuming that J is supported on the plate.
So supported associated variety is contained in here. Now let's see what happens when we do other direction. When we took ideal from here, went there, and returned. So first of all, to state the second part of the theorem, I need to describe that action of the component group So we have Q action on W, that from the beginning, from the definition. And this gives rise to the action on ideals, well, in particular on ideals of finite codimension. But then the connected component acts trivially on here because it acts by inner automorphisms. Of W, well, this means that its Lie algebra is included into W, and then these actions are compatible. Okay, so from this discussion, we have action of Q over Q connected component, and this group is nothing else but the connected component of E. This is CE, and it acts on ID fin W.
Because this is because you have a Didcot power board.
No, I don't. Well, I mean this fact.
Yeah.
Yeah.
It's the whole component.
Yes. Okay. Now the statement is, so you took I, ideal of finite codimension in W, and then you transferred it to U and returned back. So you have something like this. And this is intersection when gamma belongs to CE, gamma applied to I. Well, at least one thing that it's easy to see is that actually the image of this lower dagger map consists of Q stable ideals. So you cannot get a non-stable ideal, and this is largest ideal you can get. Okay. Perhaps let me.
Before you erase, I don't quite understand upper plus and lower plus. You have a match from ideals of W to ideals of U.
Yes.
Which is upper plus.
Yes.
And lower plus.
In the other direction.
But one of the maps is not isomorphism. The last
They're all
one.
bijections.
This is not a bijection.
Yeah, but so how do you have?
Well, I mean, we have here maps in both directions.
They're not,
There are two maps
they're not bijections.
which are not inverse. Okay. Now let me at least try to say something about a proof. Or maybe just to state the statement which is actually proved. First part is sort of easier. And the second part is much more difficult. So what you do to prove second part, we need the following claim. The claim, which I will denote by star. Well, suppose we have some ideal IH in ID UH wedge, which means the set of ideals supported on the orbit GE, whose associated scheme is completion of the orbit. So they're the smallest possible ideals. And suppose that IH is Q stable. Then there is some G sub H in IDE UH such that completion of GH is IH. So this is slightly weaker statement than the statement 2, but that's somehow the most important part of this. So when you have some such ideal of formal power series, this ideal always generated by its polynomial part. And you prove this statement in 2 steps, essentially. So first step is to prove truncated version. Star sub k. And truncated means that you take quotient by some power of h bar. So you replace UH bar with UH bar, UH wedge modular h bar to k plus 1. And then you say that I sub h in this ideal in this algebra. Now it should be both Q stable and G stable. So here we have action of G by differentiation, by derivations. And actually, if you have a saturated two-sided ideal, ideal is always stable with respect to derivations. And then we need to prove similar statement. That is that the ideal is generated by its polynomial part. And this statement is, this case is not very different from classical level when you have commutative algebras. And then you do some algebraic transformation group theory, some homogeneous vector bundles, stuff like this. And once you have proved this, you need to make step 2. And so when we proved a statement like star sub k, so what we have, we can proceed from IH bar to some IH bar k, which is the corresponding truncation. From this we will find some ideal j h sub k, intersection with polynomial part. And then what we want to claim is that g h bar is inverse limit, sort of inverse limit, of g h bar k. it's natural to take this ideal. But there is a problem that a priori this inverse limit may be empty. Somehow we need to show that this sequence stabilizes. And in fact, this is the case. Okay. Well, these were just few words about proofs, and now let me do some remarks. Actually, I want to make 2 remarks.
Is this a Reese lemma? This stabilization?
You need to construct some clever module and prove that it is finitely generated, somehow like this. So you need some finite generation of something. I'm not really sure whether this may be called Reese lemma or not, but that's basically what happens. I had 2 remarks, and these remarks are on ramifications of this theory. Well, first, these ideas lead to functors from Harish-Chandra bimodules for U of G to Harish-Chandra bimodules over W-algebra, but I don't want to give definition. Let me say that if here we have this associated variety contained in the closure of GE, then functors will be to finite dimensional Q equivariant W bimodules. And these 2 functors enjoy properties similar to properties of these maps. So they somehow a little bit fail to be quasi-inverse equivalences, something like this. And this is the first remark. And then the second remark that actually main theorem is expected to hold for a wider class of algebras. In particular, it is expected to hold for rational чередник algebras, and more precisely for the spherical, perhaps, spherical subalgebras. Well, what I mean by this so somehow my spherical subalgebra, which stuff are denoted by U sub C, is analog of universal enveloping. So U is replaced by U sub C, say of H bar W. And then W algebra is replaced by another чередник algebra. So somehow you have here ambient algebra, and W algebra is a sort of slice. But in the rational чередник case, slice is also rational чередник. And W is replaced by U C prime H over H W naught W naught, where W naught and W is parabolic subgroup. And then, for example, the component group should be replaced by the quotient of normalizer of W naught in W by W naught. And then conjecturally, exactly the same statement will hold. So here I finish.
Question concerning your second remark. Because there is more immediate generalization, namely to W superalgebras. Does the theorem hold?
I'm not sure, and the reason why I'm not sure is that I know almost nothing about superalgebras.
But it's important because the W-algebras are superconformal algebras.
Probably it's a very good problem.
I don't know.
So maybe I want to make a remark that this last thing also applies to trigonometric чередник algebras, and in which case the slice will be rational чередник algebra, but not necessarily for a parabolic, but maybe for a quasi-parabolic.
And then there are, well,
Which means that you take a Borel-de-Siebenthal inclusion. But otherwise it will be exactly the same.
maybe.
Dmitry, you wanted to ask?
At the beginning, you stated parameter description of the bijection. Is it clear that you get the same bijection as the one at the beginning?
Here?
No. At the very beginning, on the level of
Yes, it is not that easy to prove, but these are the same maps, yes. And I prove this.
And another question. On one hand, you have an ideal of finite codimension.
Yes.
On the other hand, you have a primitive ideal. So, is there any relation between a codimension of
Yes.
ideal on the left and Goldie rank of the ideal? on the right?
Not with a Goldie rank, but with multiplicity. Well, multiplicity is, well, you take associated graded, then you get some sheaf on the orbit, and you take, it's multiplicity, so the dimension in the general function.
Sasha, you had your hand up?
In the minimum important case, there is a homeomorphism between the primitive spectrum of W algebra and all primitive ideals of your G, which have infinite codimension. Is there anything, say, if we allow quotient topology on the set of orbits of primitive ideals under the actual component?
I don't know. First, I don't know about topologies on, in this good case of finite codimension or right associated variety. And secondly, I don't know what happens with, when you consider general primitive ideals.
Yeah, but can one expect at least a bijection? Can you take all primitive ideals which contain?
I don't think so.
That's what happens in the minimum method.
But
Should be true.
so I had some, how to say it? So I'm pretty sure I cannot prove something for ideals of infinite codimension using these techniques, because there are some geometric difficulties.
Any other questions?
Yeah, I have.
So you have this fact that the fibers of your map dagger are orbits under C. Is there anywhere where you could predict the size of these fibers?
There are conjectures. There are conjectures, and this should be related to recent paper of Безрукавников, Finkelberg, and Ostrich, and so there are conjectures.
Tony, you were going to
Suppose you only know that the associated variety of your primitive idea U of G contains a closure of R, but it has the right Gelfand-Kirillov dimension. Would you be able to deduce that it must be the closure?
I don't really catch the question. So we have an
Suppose
ideal.
you have a primitive ideal, and you know only that it contains a closure of a nilpotent orbit, but it has the right Gelfand-Kirillov.
What do you mean by right Gelfand-Kirillov dimension?
It means that the Gelfand-Kirillov dimension, the quotient is the dimension of the.
But then, so the associated variety coincides with the orbit.
No, because it might not be irreducible. A priori, I mean, you have to prove this, right?
Yes, but this is your irreducibility
No,
theorem.
but if you don't know that,
okay.
what I'm saying is, can you use this? It would seem that you should.
Yes.
Yes.
So actually, the proof is yet another proof of irreducibility theorem follows from this. Well, not from what I told you today, but from the paper I was talking about.
Okay, maybe we should thank the speaker again and start again in 2 minutes.